Hi class, we're moving on to chapter 8.3, Diagonalizing Symmetric Matrices and QR Factorization. So it's important to note that everything we're going to be doing in this section has to do with symmetric matrices. So make sure if you're trying to attempt this method on your own in another class for something else you're doing, make sure that the matrices are symmetric. If they are not symmetric, when we start to talk about the QR factorization, we'll talk about how to basically symmetrize the matrix. Okay, so let's go ahead and get started. We'll start off with a theorem. Okay, so the next couple of videos are kind of short, but they are also very, I guess I would call it thick. So make sure you guys are reading at the same time that you're going over these things to help them make more sense. And do, extra examples. Okay, so let's start off with a theorem. So let's say that A is equal to A transpose. So if you remember, this is the definition of a symmetric matrix, right? So if my matrix is symmetric, meaning if I take it and then I take the transpose of it, and they will be the same matrix, A being a symmetric matrix, then the eigenvectors that are associated with the distinct eigenvalues of A are orthogonal. Okay, so I'm going to try to present things in small pieces for the next couple of videos. So what are we saying here? For the symmetric matrix, all of the eigenvalues that do not have multiplicity will be orthogonal to each other. This is for symmetric matrices. This is not for every matrix. This is true in a symmetric matrix. So the eigenvectors that are associated with distinct eigenvalues, so there should be no multiplicity, no algebraic multiplicity going on with the eigenvalues. If that is true, then those eigenvectors will be orthogonal to each other. They will form a dot product of zero with each other. They lie at right angles with each other. Okay, this is very, very important. This is going to drive pretty much the rest of the class. Okay, so let's do an example. Let's start with the matrix. Also, I'm going to use this matrix many times because it's an easy one to use. So I'm going to refer back to this quite often. So I'm just letting you know that now. We will, in later videos, refer back to this matrix quite often. So we'll derive it each time for the most part, but just remember that this is the matrix I'll be using for a lot of our examples. Okay, so let's say we have a very small standard 2x2 symmetric matrix. So again, if I were to transpose this, basically flip it across its main diagonal, I'm going to get the same matrix out, right? So if I start to look at the eigenvalues, right, so I'm going to make the characteristic polynomial. I'm going to look at lambda minus A and find that determinant, right? So all of the main diagonals are going to be lambda minus the main diagonal, and then the other terms will just change sign. Okay, we've done this quite often. So when I do my determinant for a 2x2, which is very, very easy, right? It's just the main diagonal minus the product of the non-main diagonal. So we'll get this out, and then this simplifies very nicely to a factorable equation that helps me to find my zeros, right? So remember, we're looking for the zeros of the characteristic polynomial to find the eigenvalues. So I can start to build my eigenvectors one at a time, right? So if I plug in 1 back into here, so again, really what we're doing is we're setting it equal to 0, but I've been really lazy and not keeping the 0 portion of this, right? And then we're going to reduce this to row echelon form. I don't really have to reduce it to row echelon form because we can see that one row is identical to the other row, right? So I can just get rid of it and then change this to positive. So again, if there's a column of zeros here, then that's going to mean that my x1, x1 plus x2 equals 0, right? So then I can subtract x2 and I get x1 equals negative x2. Right? So again, I'm just leaving out this row of zeros. It helps me to maintain space and I don't have to write extra stuff. So again, hopefully you guys remember that we're really setting this system equal to 0 and plugging in our eigenvalue. Okay, that's what we're doing. I've been practicing bad notation, right? So my eigenvector for this eigenvalue is -1, 1, right? When x2 is 1, my x1 will be -1, okay? So I can do the same thing for x2 equals 3. I'm going to take 3 and plug it back into this characteristic determinant system, but not take the determinant. We're just going to solve for 0. And you can see I have some other dependencies here, right? So basically, if I take this first row and add it to the second row, this second row will completely go away. And I have this left over. Remember, there is a column of zeros, so x1 is equal to x2. So when x2 is 1, x1 is 1, and that is my second eigenvalue, okay? Sorry, eigenvector. Now, this theorem is saying that for distinct, okay, there's no multiplicity here, right? No multiplicity, 1 and 3, they are distinct. For a symmetric matrix, then the eigenvectors for those eigenvalues will be orthogonal. So let's take the dot product between x1 and x2. Okay, -1 times 1 is -1, and 1 times 1 is 1. Add those together, you get 0, right? So they are orthogonal to each other. Okay, so let's do a little bit more of an exploration here. Let's go ahead and take these and form them into a matrix. Okay, very much so like we are going to diagonalize it, because that's actually what we're going to do. But we have some properties that pop out from here. Okay, so put these into a matrix in the form of x1 and x2. Again, remember they need to be in the same order as the eigenvalues that we're using. Okay, actually I could switch these around if I were to continue to diagonalize it. I just want to make sure I'm keeping track of which eigenvector goes where, so that I place the eigenvalues in the appropriate sort of columns if I proceed to diagonalize, right? So I have -1, 1 and 1, 1. Okay, I'm just keeping them from smallest to greatest. You'll see later that we actually kind of want to get into the habit of going from greatest to smallest. Okay, so I'm just going to throw that out there. But for right now, it doesn't really matter what order we are. But we would like to, let's see if I can make the screen a little bit bigger for you guys so you can see what's going on down here. There we go. We would like to normalize this matrix. We're going to call this new matrix P. So what I'm going to do is I'm going to normalize this vector and this vector. Again, remember, normalize means I'm going to make it have a length of 1. Okay, so I'm going to normalize this, each vector here. Okay. Oops. So in order to normalize it, I'm going to take the vector and I'm going to divide it by its own length. Okay, take the vector and divide it by its own length. So that'll give me a new matrix that looks like this. Okay, so again, if you come back here, the length of this is going to be the square root of 1 squared plus 1 squared, which is going to be, sorry, the square root of 1 squared plus 1 squared, which is the square root of 2. And again, remember, it's going on the bottom. So the original values were -1 and 1. I'm going to divide that whole thing by square root of 2, its length. Same thing here, 1 and 1, 1 and 1, divided by its length. So now this is normalized. Okay, if I were to take the length of this vector, it would now have a length of 1 because I've divided it basically by itself, right? So we call this an orthogonal matrix. Okay, I want to be very clear here. An orthogonal matrix is not a matrix so that only the vectors are orthogonal to each other, right? Because that's what we had here. These two vectors, two column vectors, they're orthogonal to each other, but it's not an orthogonal matrix. In order to be an orthogonal matrix, you have to normalize. Okay, so I just want you to remember that now. You have to normalize. I know it does not say an orthonormal matrix, but that's what it is. Okay, an orthogonal matrix is one that the vectors are orthogonal to each other and they are normalized. Okay, so a cool thing that comes out of here is that P inverse. Okay, if I were to take the inverse of this, so I'm taking the determinant. So this is going to give me a -1/2 minus, this is going to give me a 1/2 as well, because square root 2 times square root 2 is 1/2. So here I'm going to have 1 over this is going to give me a -1, so this will be -1, and then you flip this diagonal, right? These switch places, and then the non-main diagonal, the entries switch signs, okay? So this is going to be P inverse. So if all I'm doing is multiplying everything by -1, here, in this case, I get back out my P matrix, okay? Now that's not always going to happen, but what is going to happen is that you will get out P transpose, okay? So if you have an orthogonal matrix, your P inverse of that orthogonal matrix is going to be equal to the transpose. We're going to use this quite a bit throughout the next couple of videos to do some interesting things, right? So I want you to remember this fact, okay? So let's go to a theorem now, okay? So really what we did here was we just did an exploration. We took an example. I showed you that this theorem is true. This is not a proof. I'm just picking out a random example to give you an example, right? Remember, a proof, I would prove this in general for all cases, okay? So some of you guys in your proofs are not doing too hot. Remember, a proof is not just looking at a specific example. It's looking at everything, right? So for instance, if I want to show something about vectors, I can't just pull out vectors in R2, okay? Even if it's general vectors in R2, it has to be general vectors in any size dimension, right? So just a couple of tips there. Some of you guys are, your field of vision is too narrow, right? You gotta think about everything on a general scale. So let's look at a theorem that applies to what we just did here. Okay, so again, let's look at this very slowly. If A is a square matrix that has real entries, right? So it's n by n. In our case, it was 2 by 2, such that its columns form an orthonormal basis, okay? Meaning that the vectors, the column vectors, are orthogonal to each other and they are normalized, right? So here, this A, we are pertaining to this P matrix we found, okay? So if its columns form an orthonormal basis, then A is an orthogonal matrix, right? So small typo here, it should be orthogonal, not with an A. So again, right, just what I was highlighting over here, an orthogonal matrix means that you're normalized and orthogonal to each other within your columns. Okay. So let's come to the next theorem, okay, which is also talking about this. If P is an orthogonal matrix, then P inverse equals P transpose, right? So the same thing I showed you here. So again, we just did this exploration, and I just did this to highlight these theorems so that these theorems would be a little bit easier to understand, because of course everything is easier to understand when you see a concrete example. I know you guys are having problems with some of this generalized ideas of theorems and proofs, right? So I try to throw in some concrete stuff here. But again, this is how math actually works, right? Is on a general sort of scale, okay? So what you guys are used to is more of arithmetic, right? Not necessarily mathematics. So this is like your first entrance into actual mathematics, right? This course. So let's look at a new theorem. The next one is the one that we want to use, which talks about diagonalizing symmetric matrices. So we've talked about diagonalizing matrices before, okay? So now we want to talk about if a matrix is square, then that means that you can diagonalize it orthogonally, okay? If there exists a diagonal matrix D and an orthogonal matrix P such that A equals PDP inverse, okay? This is a very, very important result, okay? This is used in quantum mechanics. I know I refer to quantum mechanics a lot, but that's one of the main uses of linear algebra, was to make quantum mechanics a lot easier to understand, but it's used in a lot of places, okay? So this PDP inverse decomposition is super important. It's also known as a spectral decomposition, okay? But we're gonna call it the PDP inverse for right now. So again, if you have a square matrix, it is orthogonally diagonalizable, meaning that you can break it down into 3 matrices, where one of the matrices is an orthogonal matrix. The other one is a diagonal matrix. Again, that will have your eigenvalues inside of it along the main diagonal. and then you have your P inverse, which is equal to your P transpose, which is nice because when we're doing the P to P inverse before, we had to actually take the inverse. Now to find the P inverse, we just take the transpose, which is computationally a lot easier to do, right? Okay, so we pretty much already done an example. Let's go back and look at what we just did, right? So I took this symmetric matrix. Okay, I have my matrix A. I found its eigenvalues. I found its eigenvectors. I threw its eigenvectors into a matrix, which we normally would call P, right, when we were diagonalizing before. But now since we're talking about symmetric matrices, and we're trying to orthogonally diagonalize things, we normalize this, right? So now I have my P value. So if I have P, then that means I know P inverse, because P inverse is just P transpose. And in this case, P transpose and P are actually the same. This is not always the case. It just happened to be that way because of the matrix that I chose. Okay, so I have all of the things I need to finish this diagonalization. So as a quick check here, what I'm going to do is I'm going to have P, okay, which we found, times the diagonal, which is 1 and 3 along its diagonal, times P inverse, which is the same thing as P transpose, which in this case is the same thing as P. So remember, you are taking a matrix and you're factorizing it, okay? That's what a decomposition is factoring. Just like if I had the number 6, I could write it as 2 times 3. I'm breaking this matrix down into fundamental pieces so that if I needed to use this for some computations, I can just do computations on single parts of these or, you know, group things together. It makes it easier to look at something when you can look at its parts, right? If you think about a super long, let's say 8-term polynomial, okay? If you can look at that polynomial in terms of its factors, then you know a lot about that polynomial. You know when it's 0, you know when it's going to cross the graph, you know when it's going to bounce off of the graph due to the multiplicity of the zeros. You can talk about the end behavior, you can do all kinds of things if you take a polynomial and break it down. That is the reason we're taking these and breaking it down as well. Computationally, it takes up less time to do things with this matrix for what we need to do, and the pieces that we are breaking it down to tell us certain things, okay? We're not going to get too deep into it now, but we will in a few later videos, right? But for instance, I know from this decomposition what my eigenvalues are, I know what my eigenvectors are. So now that I have this, if I wanted to, I don't know, solve a DE that's associated with it, I have those pieces, okay? There's other things that we do with these things, but again, these things tell me stuff, right? If I want to know the rotation that happens due to using this as a linear transformation, now I have some of those pieces for me as well, okay? So there's just certain things here that's nice and interesting for us to do. So remember, when you get to this point, you can always check your work, and you should always check your work. Multiply PDP inverse and see if you get out A, okay? There's been several times, even as I go through these examples with you, or prepare these examples on my own, where I multiply these things out and I'll get something like 2, 1, 1, and then this will be like 19 over 10. So almost 2, but off a little bit. So I made a mistake somewhere in my P or my P inverse, or you know, there's a small mistake somewhere where I need to go and fix that. So I can check if there's mistakes if I double check my work by multiplying these 3 matrices out in the correct order. Okay, so you can always check your work here. So make sure you guys take advantage of that. So let's look at the next thing. Okay, the spectral theorem. Okay, so this is another very important theorem. Notice that this has an actual name. Okay, so that's one big clue. Whenever a theorem has an actual name attached to it, and not just theorem, it's super important. Okay, so this, I remember using this several times. Maybe there's like, I could easily count probably like 8 different classes where this was presented over and over and over again, right? So The spectral theorem is a very common theorem that pops up in applications. So let's get to it. Okay, so a matrix is orthogonally diagonalizable if and only if it is symmetric. Okay, so we can only diagonalize a matrix into this PDP inverse form where P is an orthogonal matrix or orthonormal, right? And where P inverse is P transpose because it's orthogonal, if that matrix is that you're decomposing was symmetric. Okay, so this is only going to work for symmetric matrices. Now, we can diagonalize pretty much any matrix, okay, but we can only diagonalize symmetric matrices orthogonally, okay, meaning that those column vectors are orthogonal and they are normalized and it holds all the properties that we've been talking about. Okay, so we have some corollaries, right? So what a corollary is basically because of this theorem, there are some lesser but still important kind of conclusions to come from this theorem, right? So one of the corollaries is that eigenvalues of symmetric matrices are always real. Okay, so if we have a symmetric matrix, you're not going to have to worry about complex eigenvalues and eigenvectors. So that's nice because I know you guys were not having a wonderful time with that, right? And the second corollary that comes from that spectral theorem is that the dimension of an eigenspace for a symmetric matrix is equal to multiplicity of the eigenvalue, which is nice as well. So if your eigenvalues are distinct, then each of those are only going to have one eigenvector. Okay, if you have an eigenvalue that has an algebraic multiplicity of 3, remember what we said before, that you can have 1, 2, or 3 eigenvectors from that 1. Okay, so here it's always going to be equal to that multiplicity. So if you have an algebraic multiplicity of 3, you're going to have a geometric multiplicity of 3. Okay, it will not be anything less than that. It will be equal. So that's nice. Okay, because now you know how many eigenvectors you should be getting out from each eigenvalue. Apologies. Okay, so here is another theorem. Okay, I know you guys love theorems. If you have a matrix that is not square, okay, then every eigenvalue of A transpose A is not negative. Okay, so again, you're going to have only positive eigenvalues from A transpose times A. This is actually a really, really big deal. This is going to allow us to basically diagonalize matrices that are not symmetric, okay, or that are not diagonalizable, right? So let's look at an example for this. Okay, and again, this is going to be a symmetric matrix. Okay, so let's consider A. Okay, 1, 2, 0, 0, 1, negative 1. Now, if I take A transpose A, that means I'm going to turn this and rotate it 90 degrees. I'm going to put it on its end. Okay, and I'm going to multiply it times its original self. And so now, notice I have dimensions that match up. Okay, and I'm going to end up with a 3 by 3 matrix. If you look at this 3 matrix, 3 by 3, it's symmetric. Okay, my main diagonal can be whatever the hell it wants to be, but then the values opposite the main diagonal are symmetric. Okay, so if I were to take the transpose of this, I would get the exact same thing out, which now means that to this result, I can come back and I can apply the spectral theorem. Okay, which is basically what we're going to do. So we can find the eigenvalues for this A transpose A by doing what we normally do, right? So we can put this into its determinant form. So we're going to subtract the main diagonal from lambda, and we're going to change the sign everywhere else. And so we can do this we have a couple ways, right? So I normally do the 3 by 3 method. I think here I decided to go ahead and do the expanded form for the determinant. So I have, okay, so let's look here. I am going through this way. Okay, so right now I'm starting here. starting at this row. Oops. -1, 0, -2, 1. Sorry guys, 0, -2, 1. So I'm going down this way. Oops, sorry, I'm starting here. I'm coming down this row. Apologies, you guys. I didn't know which direction I'm going. So I'm going here. So the first term is 0, so that's nice because I don't have to do anything. So the next one is I'm choosing this. So this column goes away and this column goes away. And I'm left with this one, this one, this one, and this one, right? Which is what I have. Okay, I had to look at that real fast. So remember it goes positive, negative, positive. So this is positive, negative, positive. So that's why I have a -1 in front here. Okay, and then the next one will be this term, and then these values disappear, and this is the sub-determinant that I'm going to look at. Okay, so my row expansion. So I have, this is my equation, right? This is my sub-determinant plus that value, that cofactor expansion is what I was looking for. That's the term. So this is the cofactor, and then that sub-matrix I'm taking the determinant of. Okay, remember 2 by 2s are pretty easy. This has a 0 in it. So I'm going to get a negative lambda minus 1 plus lambda minus 1 times these two minus a 4. Okay, so this is what I'm getting from the first determinant, negative. I have this product. This one goes to 0. Then I have lambda minus 1, lambda minus 1, lambda minus 5. And then I should have a minus 4 times that value as well, right? Because remember, I get the lambda 1 times everything. So notice here, right? I could multiply everything out and condense things, but right, we try to work smarter, not harder. Everything here has a lambda minus 1 common term. So I can just pull out lambda minus 1. And I'm left with minus 1 of them here, minus 4 of them at the end, and then the 2 that are left over in the middle. Okay. And then from here, I can start to simplify. So here I can add these two together and get a -5. And then this is super easy to multiply out. Okay. And then notice that the 5, the -5 goes away. So then I'm left with lambda minus 1, lambda squared minus 6 lambda. Those constants disappear, right? After multiplying this out and adding that -5 in. And it's pretty much factors itself, right? So this wasn't too bad. So I have lambda times, sorry, this should be lambda minus 1. Okay, so I guess that's one typo. And then this is going to be lambda minus 6. So my zeros are 0, positive 1 from the lambda minus 1. Not just minus 1. Right, lambda minus 1 here. And then the positive 6. So all of these are larger than 0, right? Which is what we said from our case here, right? So if you have a non-square matrix, okay, then every eigenvalue of A transpose A, which ends up turning into a symmetric matrix, is going to be non-negative. And that's also because we have here that eigenvalues of symmetric matrices are always real. We had another theorem somewhere that said that they're always positive, didn't we? No, we said they're always real. That's right. Okay, but A transpose A will always have a non-negative eigenvalues, which is nice. So that's what we just kind of showed here with an example, not a proof. Okay, and that's all, right? We can take this further and we can finish trying to diagonalize it, which is actually what we're going to get into next, which is the QR factorization. Okay, so the QR factorization is how we sort of decompose a non-square matrix. Okay, so we can QR factorize pretty much any non-square matrix. Okay, when we have a square symmetric matrix, then we're using the orthogonal diagonalization. All right, so let's get into it. So this is a little bit of a thick notation as well, so let's kind of read through here. So let's say we have a matrix A that is n by m. So each of these vectors have n components, and there are m of them, right? So n rows, m columns, okay, because there's m vectors, right? Rows by columns. So A1, A2, up to AN, there should be some columns here. These are all linearly independent, Okay, they're linearly independent from each other. You cannot make any one of these from any combination of the others. They're all independent. Okay, then there's going to exist a matrix Q, right? So there is just as many column vectors in Q as there are column vectors in A, right? So the dimensions of Q is the same as A. They're the same size matrix. Here, each of the elements Q1, Q2, Q3 through Qm are going to be orthonormal, meaning they're all orthogonal to each other. Okay, they form an orthogonal set, and each one is normalized. Okay, so again, this is very, very similar to what we just talked about for the orthogonal diagonalization, right? And we are going to have a matrix R that is square and upper triangular. Okay, so your diagonal is going to have entries, and then everything above it is going to have entries. All of those entries are going to be positive. Okay, and if I take Q and multiply it times R, I will get A. So what we're saying here is I can break A down into an orthonormal matrix. I'm sorry, an orthogonal matrix, I should just say, right? So the column vectors are going to be orthogonal to each other. They're going to be normalized. And I can multiply that times R, which is upper triangular with positive entries. So this decomposes into an orthogonal matrix and an upper triangular positive matrix. Okay, so that's our factorization for things that are not square. Okay, so let's go over the steps. Okay, so I'm sure that the orthogonal diagonalization isn't too much because it's very similar to the diagonalizations we were doing before. QR factorization is a little bit different, but not too much. So for this one, we're going to go over the steps. Okay, so how to find the QR factorization. First, we're going to apply the Gram-Schmidt process to those column vectors. Okay, so again, I need these things to be orthogonal. I can't do eigenvalue stuff because it's not a square matrix. Okay, so since it's not a square matrix, I'm going to make these into an orthogonal set, and then I'm going to normalize them. Okay, so that's how I find Q. I Gram-Schmidt these to make them orthogonal, and then I normalize them, and that will give me my orthonormal set of vectors. Okay, so that's how I find Q. I just Gram-Schmidt A, the column vectors in A, and then I normalize them. Okay, now Q being orthonormal implies that we have certain properties, right? Which is that the Q inverse is equal to Q transpose, right? So the inverse equaling the transpose, as we saw before with that P matrix, means that if I multiply Q transpose times Q, I'm just going to get the I matrix, okay, the identity, right? Here I put M columns, and that's basically what's going to happen because now I have a square matrix, right? Transpose times a regular matrix gave me a symmetric matrix. In this case, that symmetric matrix is the identity matrix, okay? So from the result that I want, A equals QR, I can pretty much kind of solve for R, right? So if I multiply it by QT on the left on both sides, it looks like this. Q transpose A equals Q transpose Q. But what's Q transpose Q? That's the identity matrix, right? So that gives me R is Q transpose times A. So all I really need to do is find Q. Okay, once I find Q, I can find R very easily, and then I'm done. Okay, so I'm going to Gram-Schmidt my A. I'm going to normalize that result to get Q. I take the transpose of that and multiply it times A to get my R. Okay, not too bad. So R is Q transpose A. So let's go ahead and go through that process. Okay, so the first one, let's find the QR factorization for A. So if you notice, this is the same A I had way back here. I'm gonna really just be using the same matrices over and over again, right? So this is the same A, but I'm taking that transpose of this original. Okay, so there's no link between what's going on here and there. Okay, I'm just letting you know that's the matrix I decided to choose. Okay, so I'm gonna let this be my A. Okay, because I'm lazy. I didn't want to make a whole new one. So here my first column vector is A1. Okay, and my second column vector is going to be A2. Right? So I apply the Gram-Schmidt process to these vectors to find my Q. So for Gram-Schmidt, the first one is the first one. Okay, that's nice. And the second one is going to be the projection of A2 onto A1. Right? So remember how that goes. You take the A2, you subtract the dot product between these over the length of the one you're projecting onto times the one you're projecting onto. Okay? So dot product between A1 and A2 in this case, because that's my V1, it's the same as A1. It's going to be 0, 0, 2 on top, and then the length of V1, which is the same as A1, is going to be square root of 5. Okay, sorry, not square root of 5, but 5. Right, 1 squared plus 2 squared, no square roots because we're squaring that. So I got A2 minus the projection term, okay, onto that vector I'm projecting onto, which is A1. Okay, so when I simplify this, this is what I get for V2. Okay, so then my set is going to be basically A1 or V1 in this, right? So V1 and V2 is my set of vectors, right? So that's what that looks like as a matrix. But that's not Q yet, because Q is the normalized version of this, right? So I got to normalize each one. Okay, so I just go through that real fast, right? So the length of V1, if we go back to V1, is square root of 5, right? And then here the square root of this, or I'm sorry, the length of this is a little bit more involved. You can do that on your own to check. But basically I'm taking each of these and dividing it by root 5. Here, this matrix, oh, I did work it out. I guess I'm a nice guy, right? So here I can simplify this. So this is 1 over 5 root 30. Okay, and then I'm going to multiply that across here. So then I'm going to have some not as nice things, right? I might have 1 over root 5 times. I think I did this wrong. I think this should be root 2 25s. I think these values are off, you guys. Okay, so apologies. This should be root 1 over root 30 over 5. So I'm looking, I wrote it as 1 over root 30 is the fraction, the numerator, and 5 is the denominator, when really 1 is the numerator, root 30 over 5 is the denominator. Okay, so it's just the notation so that this is correct. Okay, so if we do, that's what, it's 1 over the length, right, times the value. Okay, so these two vectors are correct. So when I multiply 1 over root 30 over 5 in, the root 30 over 5 flips, so this is really 5 over root 30. So the 5's cancel on both of these, and then you got 2 over root 30 negative 1 over root 30, and then this is negative 1, so you multiply that times the 5 over root 30, and this is what we have. Okay, so now we have my Q1 and my Q2. We can put these together to form the Q matrix. So Q1 is here, Q2 is here. They are orthogonal to each other, and they are both normalized, so they both have a length of 1. Okay, so now in order to find R, what I need to do is I will multiply the transpose of Q times A. So again, I'm going to transpose this thing. So instead of a 3 by 2, it'll be a 2 by 3, and multiply it by the original matrix A. So transpose Q times our A matrix, and so when I multiply it out, I should get a 2 by 2 out, and this is my result. So obviously I've done this very fast because it's all written out, but you should definitely do the math to double check to make sure that this is what we get, right? So I guess we can go over real fast. I have 1 root 5 plus 4 root 5. It's 5 root 5 and nothing here. For this one, I'll go this vector times this vector, right? This row vector and this column vector. So I got 0 times 2 root 5 times a 0. So 2 root 5. For this one, I have what's going on here. So here is a 0. This is a negative 2. And these two give me a positive 2. So that cancels out. And for the last one, this has no part in it. This is a 1. And this is a negative negative. So that's a positive. So I got 1 plus a 5, which is 6 root 30. So again, don't get thrown off by these radicals. I'm like, oh, this is so much math, it's so hard. It really isn't. It's all common denominators when we're doing this, right? So you're really just adding the numerators to get to your result. So again, notice that R has all positive entries and it is upper triangular. Okay, it has diagonal entries and values above the diagonal, nothing below the main diagonal. Okay, so R is upper triangular with positive entries, and A is Q times R. So we're just going to check real fast. So I'm going to take Q, I'm going to multiply it times R, right? And I should get out my matrix A, right? And there we go.